Hi everyone, my name is Shorjit Mazumdar. I'm a high school senior from William Fremd High School, and my PECI presentation or paper concerns the robustness of communication-free VOC inverters versus communication-based load-sharing inverters with side-channel noise intrusion. Um, so to begin with, I'm going to go into a little bit of background and then launch into a description of the research specifics, like the research process and results, etc. So to begin with, this project was concerned with, or the motivation stemmed from the fact that the grid is currently transitioning from centralized generation relying on fossil fuel sources to distributed generation relying more heavily on renewable sources. And this necessitates the synchronized operation of multitude of inverters to prevent grid instability. And so this explains the synchronization aspect. But in regards to self-synchronization or the need for self-synchronizing inverters, the synchronized operation of conventional inverters has generally made communication for synchronized coordination quite vulnerable to cybersecurity threats. And so with this, recently at least, communication-free self-synchronizing inverters, an acronym I dubbed as CFSIs, are based on a novel virtual oscillator control methodology, which have gained sort of popularity in recent years because this methodology appears to enable decentralized operations of such inverters, and therefore by operating on a decentralized level and not on a global sort of network, this appears to reduce vulnerabilities to cyber attacks. And so the diagram on the right illustrates that idea with a contrast between communication-free inverters versus communication-based inverters over our AC grid. And so this formed the sort of core basis for the research problem or research investigation. And this was the fact that even though virtual oscillator controlled based inverters do not communicate with each other, they still make local measurements. And so the research focused on the fact that how can we tamper with these measurements using electronic noise that simulates a cyber attack in order to demonstrate the impact of sort of the impact of noise on the synchronization of these inverters. And as such, recently, actually, we explored this vulnerability in a paper in the IEEE Transactions on Power Electronics publication that was published recently that explored this issue. First, how to demonstrate that noise is a problem, and then after demonstrating so, finding a novel application to mitigate the impacts of this noise. This paper, first submitted to the PECI conference at the University of Illinois Urbana-Champaign, extends this research by essentially exploring how noise affects the performance of this parallel inverter in contrast to a communication-based load sharing control or a LSC inverter operation. And so this is a study essentially of contrasts between the two inverter operation behavior. And just to give a quick bit of background, self-synchronized coupled oscillators. So when I refer to this notion of self-synchronization between inverters, what this first means is that an operation or a network of inverters can be run using conventional circuit theory, where we can define the synchronization condition in the sense of the bolded statement, in which the limit between any successive pair of inverters in this network, the limit between the difference between the output voltage is zero. And so this is the first synchronization condition. But to be more specific in this case, in this practical or in this paper, using a virtual oscillator control implementing such an inverter, we can see that as depicted in the diagram on the left, in order to operate these inverters, these communication-free inverters at the frequency of 60 hertz, emulating the grid frequency in the United States, each inverter in this lab or in this paper was controlled using a virtual oscillator control method, which is implemented in our digital signal processing platform, our DSP. And I'll show the experimental setup in just a few slides. But essentially, the reason why this is called a virtual oscillator control is because the coupled oscillator or the notion of a coupled oscillator is implemented virtually. It's not implemented physically. However, but because this inverter is providing current to the load, this current is scaled when sent to the when the two inverters share a common load, as depicted in the middle here, along with noise injection sites depicted, and with the virtual oscillator control feeding into the inverters. So that provided a sort of layout, but then we can see here that that the output of each inverter will be close to a sinusoidal waveform in order to mimic the 60 hertz AC grid. And the way this is done is by closely following a mathematical sort of derivation for an oscillator. And so we can rely on recent literature covering Lenard's theorem, which states that a Lenard oscillator follows the form of the second derivative of V plus R of V times V dot plus M of V equals 0. And as I'll show on the next slide, these conditions guarantee a stable limit cycle, which is what we are interested in order to demonstrate how inverters can synchronize to a common frequency and how that synchronization can be disrupted. So what we can see here is that this plot on the right here, this is a phase plane plot of the derivative of the voltage versus the voltage. And as we would expect, we can set up these equations on the left here, these second order differential equations using circuit theory. And what we can see is that a parameter from a sort of review of literature, we can develop this parameter called epsilon that is sort of a encapsulation of things like our virtual inductance, capacitance, and resistance. And in order to minimize the effects of sort of distortion or a deviation from the synchronization to the 60 hertz frequency, we can plot the effect of changing epsilon on this phase plot on the right here. And what we can see is that as this distortion parameter is increased from 0.1 to 3, and increased in general, this disrupts the stability of the limit cycle. And this is sort of the central point of investigation in the research. And so this sort of brings us to the intellectual merit of the overall research, in that we can see that the impact of feedback information uncertainty in general is quite new. Yet at the same time, we can see that in the presence of, especially in the past few years, increasing cybersecurity threats, we can see that the risk by not understanding this information uncertainty and exchange between local exchanges of information between inverters necessitates a closer look. And so the paper cited here, just published last month, actually, basically demonstrated the actual experimental validation of the impact of this electronic noise, as well as the application of an algorithm to mitigate the impact of this noise. Again, what this paper does for the PECI conference is a case study in demonstrating and comparing the effects of noise on the operation of a load sharing inverter compared to a virtual oscillator control-based inverter, in order to demonstrate which one is more robust or immune to the effects of noise. This is just a quick overview of the research process followed. Essentially, a MATLAB model in Simulink was developed over the course of several weeks. And then based on the simulation results developed in there, an experimental setup was produced where results were collected in order to demonstrate the effects of noise first on a single inverter in a standalone configuration, and then in the second case in the parallel configuration with two inverters. And what we can see is that the impact of noise on a single inverter is plotted here, where we can see in plot B, when the VOC voltage is plotted in blue, versus the control measurement of sorts with the VOC voltage without noise plotted in red, there's a significant distortion, and this demonstrates the effects of the noise, where we can see that the inverter is no longer able to converge to the single stable limit cycle of 60 hertz. And this is shown in the time domain results at the bottom. We can also see this is true in the case of two inverters, which is what the majority of the paper is concerned with. As we can see in plots C and D, where we look at the output and current of inverter 1 and inverter 2, we can see that as the noise is increased significantly, the sort of bandwidth there, or the distortion of the second inverter output current, has increased significantly, which again demonstrates a loss in synchronization in first the local sense, in converging to a common frequency between inverters, as well as the fact in a global sense where no inverter in the network is able to converge to a stable 60 hertz limit cycle. So then we can look in the time domain and understand, based on the bottom two plots, where the first two represent the output currents, we can see that in the difference in the output currents of the two inverters, which allow us to more qualitatively capture the effect of the noise, we can see that in the case where 15% of the current is sort of injected in terms of the noise amplitude, we can see that the steady state performance has significantly deteriorated to the point where there are large deviations, almost to the order of 2 amperes, between the output inverter currents. However, in the load sharing scheme, so this is just a quick overview of the scheme, sort of referred to from recent literature, where we can see that each inverter has an internal voltage loop control. And we can see that this essentially allows us to compare a reference voltage for the inverter output to the feedback voltage of the inverter before this is fed into a PRC compensator, to generate a desired modulation signal. And so this is just a quick overview or like a schematic of the sort of methodology used for the exact load sharing configuration. And what we can see here is that because the communication-based inverters are coordinating with each other, the noise will affect, once injected in one inverter, the dynamic of the other inverter as well. The difference between this and the virtual oscillator control method is that while there is no coordination over a communication network in the load sharing control case, we can now explore, because there's global communication and global interchanges, how this coordination may have a positive impact or not. And we can see in the time domain result, this time for the load sharing configuration with 2 parallel load sharing inverters, we can see that what's quite interesting is that plotted in the third part with the difference in the output currents of the 2 inverters, we can actually see that the performance of the load sharing based inverter performed better than the virtual oscillator control based scenario. And what's interesting is that even though it appears that the virtual oscillator control operation should have an advantage because they don't require significant global communication, we can see that the noise actually deteriorated based on the results on a couple of slides ago, the VOC parallel system. While in the load sharing system, we can see that the difference in output current is only on the order of about 1 ampere, which is almost twice as good as the performance of the virtual oscillator control-based system. And intuitively, this kind of makes sense in the sense that we can explain this behavior because the virtual oscillator control necessitates an attraction of each inverter to a 60 hertz synchronization frequency. And this is directly affected to the noise even at the local level. And therefore, the synchronization quickly unravels and is lost. And so in conclusion, what this paper demonstrated is that for the first time in the previous paper cited in reference to, that while these oscillators normally nominally in the VOC methodology self-synchronize to a common output frequency without any sort of global communication, this ensures that their synchronization is vulnerable to electronic noise simulating cyber attacks in their local feedback. What this paper demonstrated for the first time is that the virtual oscillator control in a case study compared to the load sharing communication-based inverter could actually be more susceptible to some cyber threats, which presents a potential drawback with implementing this methodology or class of inverter. And it appears that physically this happens because of the coupling of this inverter network, even though there is no global communication between the inverters. While on the other hand, in terms of why the load sharing inverter configuration performed better, we can see that this reduced the impact of the inserted electronic noise on the operation of the network, because the parallel inverters share output currents with each other, and this coordination actually helped to reduce the impact of the electronic noise. And just to end on the note of future work, potential broader impact, it can be conjectured that the issues explored in this paper for the VOC-based inverter are also relevant to other classes of self-synchronizing inverters, which would be interesting subjects of future investigation as to the efficacy of these methods. And on the other hand, we can see that these results may be applicable to defense and commercial applications for things like electric or hybrid electric ships, electric aircrafts, EVs, etc., when considering what type of communication network is ideal to implement in such a crucial scenario. And so Finally, here are just the references that were cited in this presentation. Number 2 was the reference that I was referring to sort of throughout the presentation that was published last month. And finally, thank you everyone for listening to my presentation.